can move to the next presentation. Will be given by Dr. Haobo from RMIT University from Melbourne, Australia, and Dr. Lee will talk about recent advances in ground-based GNSS atmospheric monitoring, new dataset, methodologies, and emerging applications. Please.
Thank you, Chair. Hello, my name is Haobo from RMIT University in Melbourne, Australia. And today, many thanks for the great chance to stand up here to provide you with a brief update about what we have done over the past few years. And we've also RMIT's flag. And the topic here today is recent advances in ground-based GNSS atmospheric monitoring. So when I talk about recent advances, I'm referring to dataset, methodologies, and also applications. So I'll provide a brief review of this topic. Here's the outline. I will start by the background motivation and then the three key parts, the generation, analysis, and applications of ground-based GNSS atmospheric parameters. And finally, I'll end up by giving you the summary and outlook. So I'll quickly go through here because I think everyone knows the importance of the detection and monitoring of weather and climate extremes, because it has already posed significant risks on human society. And I'm presenting some numbers or figures here, but things are changing so rapid. So I believe the numbers are subject to change somewhat. And but the key message here is we should mitigate their detrimental impacts. And the second motivation here is about water vapor. As one of the most active greenhouse gases, it contributes to 60 to 70 global warming. So we should conduct accurate or continuous monitoring of water vapor. And the third motivation, I think, is closely aligned with the topic of this session, because you can see GNSS as a sensor of the atmosphere and space weather. So we hope to utilize the capability of ground-based GNSS atmospheric monitoring to monitor water vapor. And if we can have a long-term historical data, we can find the signal inherent in the long-term data. If we can have the nearer time or real-time data, then we can serve the meteorological community. And the last one, I think, is the proven value of these parameters in these communities. Okay, so let's go to the first part, the generation of the dataset. And I will introduce first about our recent work. This was published in last year, late last year, in Earth System Science Data, and it took us actually 6 or 7 years to complete this part. And so you can see the highlights here. The data set include 5,000 plus stations, and the duration is up to 22 years from 2000 to 2021. But I want to clarify here, this is constant work, ongoing work, and we're still expanding the duration of this data set. So it's still continuing work. And the temporal resolution is hourly, and this is subject to quality control using some external references. And also, apart from the data set, we also got some derivatives like the minimum, maximum, mean value, or climatological standard normals. We also use pentat, decad, or monthly duration range. And to ensure the dataset is freely or accessible or available, so we developed this portal, and so everyone can just register an account. I'll leave this for a while because for the right panel, you can see I just got a screenshot because this workshop, it happened in San Diego, and I just got a screenshot of the station SANT, and when you press the dots here, you can see the details, like the station, like the longitude, latitude, height, and also duration, the data completeness or integrity. So that's something that I hope if you are interested in this work, then you can have a look. So apart from the long-term historical reprocessed data, we also got a comprehensive, data processing platform, and through our collaboration with industry partners and also government stakeholders like the Bureau of Meteorology in Australia, and so we got the final products, rapid products, near-time products, and also real-time products. As I mentioned before, this is also a continuing work. So that's the generation of data set. Then I'll move on to the analysis of this data set, because if we have the data set, that sets the foundation of our work. But what we hope to do for the next step is just to figure out the correlation among genetic data and also meteorological data, and also its correlation with climate or weather extremes. So that's the second part. But in this presentation, I just put some preliminary examples or case studies. So let's start first. This is statistical analysis. It's just figure out the interrelationship among you can see 2 genetic data, 8 meteorological data, and also 2 statistical parameters like the day of the year or hour of day, just figure out the temporal correlation. And we use the Pearson and Spearman's ranking correlation coefficient to figure out their difference for linear or monotonic relationship among these variables. And the second part, we move on to the principal component analysis, the PCA. This is also a statistical analysis. The key aim here is to figure out whether the combination of the, let's say, 12 variables can be effectively used to distinguish or classify different types of heavy precipitation, different types of precipitation. So you can see the 4 different scenarios: heavy, moderate, slight, and no precipitation. So we can see from the left panel, it's quite clear that if we use the combination of these parameters, we can clearly distinguish these different types of precipitation events. And based on a further analysis, we can see the genetic parameters and also cloud coverage are the key variables or contributing factors in this classification. And the third part is the time series analysis. This is quite simple. I think everyone knows that, because if we figure out, do the comparison of the PW or ZTD time series with, the formation of heavy precipitation. So we can see there the common rule during the evolution of most heavy rainfall. GNSS data typically increase considerably to reaching a larger value, or we can say it's a peak value, then decrease rapidly, but before and also during heavy rainfall. So here's an explanation or interpretation from the synoptic perspective. So the strong water vapor transport actually means the large increase. And the convergence upward motion process, during which the water vapor condenses into cloud droplets, so it actually means a sharp decrease in the GNSS parameters. And when the cloud droplets grows and fall as raindrops, that's the formation of heavy rainfall, let's say. Finally, it's applications. I will include 5 different parts. So the first part is about the nowcasting or very short-range forecasting of heavy precipitation, because I list the weather extremes here because I simply select heavy rainfall as a typical case study for the weather extremes. So for the first part, it's some statistical models. This includes the different types, like the threshold-based model, anomaly-based model, or cumulative anomaly-based models. So I want to say something here about cumulative anomaly-based model, because the heavy rainfall in particular reflects cumulative effects instead of instantaneous features. So I think cumulative anomalies are quite useful in the detection of heavy precipitation. And but the key question here is how to define reasonable normal cycle, because every time we use when we hope to calculate the anomaly time series, it's important for us to remove the normal cycle from the raw observations. So how to define a reasonable normal cycle, or make it adaptive, or for the different regions for different periods. So that's something we need to resolve. Apart from the statistical models, here's a neural network-based model. I believe we know that there are a lot of things happen over the past few years about the development of neural network-based model or AI-empowered models in such analysis. But this is quite simple, and this is quite early study. The reason why I hope to do this is just to test the utility of the neural network, like say back propagation neural network in the development of weather heavy rainfall detection model. So the input is quite simple. We include genetic parameters and also meteorological parameters. Then the output is a probability of heavy rainfall occurrence. So the main issue here is how to interpret internal mechanisms and physical processes. But I think there are lots of progress here. And the third part is, I think, the most important part because the operational model is a numerical weather prediction model. In Australia, we have the access model. So the motivation here is not to simply, assimilate GNSS data into the model to improve the precision or accuracy of atmospheric fields or weather detection. The main aim for this study here is to determine the optimal spatial resolution for assimilating GNSS atmospheric parameters. I think that's quite important because previous studies simply adopt all the stations without optimization and simply put them into the model and then assimilate it into the model to see whether there's some improvements or. But I think that's not the optimal or best practice. So for this type of study, we can also evaluate the adequacy of the existing infrastructure. It's not for PNT, but also for for the meteorological or climate studies. And so for the data, we use the RMIT near-time data platform. We use 80 stations. We also use the data thinning strategies based on different schemes. We have 6 different schemes. And also we use the iterative 3-dimensional variational data assimilation method. And the optimal resolution we found for the Victoria state is 46.4 kilometers. I do not think this is a universal value, but I strongly advocate everyone just if we hope to conduct such studies, just do this feasible or feasibility analysis before assimilating GNSS data into the operational model. And yeah. So the second application is improve the quality of a meteorological variable. Here I also place an example here is a potential evapotranspiration. And the main motivation here is we find that the combination of GNSS and atmospheric or meteorological parameters shows strong linear correlation with the PET difference. Because it's a normal practice for us to calculate PET using 2 different types of models, whether it's a Thorn's-Waite model or Payment-Mountains model, but they both have their benefits and also disadvantages. So what we hope to do is to combine them together to utilize GNSS parameters to improve to calibrate the PET derived from the Thorn's-Waite model to ensure it can have the higher match the accuracy, the precision of those derived from the Payment-Mountains model, which is more complicated. And this is a quite simple one. And the third application here is detection of climate extremes. And for this part, we also select the flash drought as a typical case study. And flash drought it actually means the rapidly evolving drought with sudden onset, short duration, high impact. But how to extend the detection lead time is quite important at this stage. And for the evaporative divine drought index, is the EDDI, is a promise index for early warning and quantification of flash droughts. So, but now it has a quite limited, precision. So what we hope to do is to combine together. We also use the GNSS data to calibrate them, the PET, and based on the high quality PET, then we can derive high quality EDDI. Then we can apply the EDDI to flash drought detection. So it's quite straightforward, but we can see the performance is quite good because we have already extended the lead time to 38 days. I think that's quite promising. And apart from flash drought, we also collaborate with Australian Bureau of Meteorology to develop a disaster risk analysis app for drought in Papua New Guinea. This also collaborate with the governments to help ensure the monitoring of drought events in Papua New Guinea. And the fourth application is monitoring atmospheric circulation. I know there are a lot of studies that just try to monitor, atmospheric river using GNSS data, but for this typical study, this is not that case because you can see this case study is actually affected by the Hunga Hapai volcano eruption near New Zealand, and also affected by tropical cyclone Cody. And what we hope to do is to utilize GNSS data like ZTD or its gradients and also the crest and its derivatives, different types of variables to ensure we can monitor the migration of water vapor. And finally, is other analysis. There's some recent studies. For the first part, it's about motivated by the Southern California wildfire last year. And what we hope to do is to ensure whether we can find some precursor information contained in GNSS data before that event. Or we can also figure out how long it should take us to recover from that type of event. And for the right panel, it's also a recent publication in GPS Solutions. It's a characterization of PW behaviors stratified by the Copenhagen climate classification. So this one is we use 1,000 plus stations to figure out their behaviors in different climate zones. So that's another type of analysis. So for the summary outlook, what we can get from this, I think just based on some preliminary case studies, based on some typical cases, I think we can find the data generation, data analysis, and some different types of applications of genetic atmospheric parameters. And where do we go from here? I think the first part, if we can get the high quality near-time, real-time genetic data, we can make them useful for weather forecasting or nowcasting. If we can have a long-term historical data, we should harness the capability of AI, like AI enhanced mining of the long-term historical data. And we should also enrich the data assimilation and numerical weather prediction community. That's something we should collaborate with the meteorology administrations. And the fourth part, in innovative applications, the last part, this is interdisciplinary research, so seeking interdisciplinary collaboration. And the right figure, it's also a recent paper published by us, also collaborate with the WMO officers. Also, we hope to spotlight some key barriers and also future directions for this type of research. So that's all for my presentation. Thank you.
Thank you very much.